Okay, good morning and good afternoon to those of you on the European, African, or Asian time. And thanks for joining us today. In this webinar, myself, Hamid Al-Mohammed from Radiant Earth, and Dr. Kai Sander from CGIAR Big Data in Agriculture platform will talk about a ground reference data guide that is developed as part of a community effort to enhance machine learning applications, particularly with Earth observation data. Our agenda today is that I will give you an overview and summary of the guide, and then Dr. Sander will present from their work at the CGIAR with ground reference data, and then we will open it up to discussion and Q&A with all of you. So feel free throughout the discussion to enter your questions in the Q&A panel. On the webinar, you should see a Q&A sign. So feel free to enter your questions there. You can also upvote others' questions. So if there's a common question, you can upvote that, and we will definitely get to those questions during the Q&A. So as I briefly said, my name is Hamid Al-Mohammed. I'm the Chief Data Scientist with Radiant Earth Foundation. And this guide is basically an outcome of a one-year project that we have been doing on ground reference data, particularly for agricultural applications. And it will be an ongoing effort for Radiant to push forward this as a community standard and revising it based on the feedback we will receive from the community. Before getting into the guide, I'm going to briefly discuss and introduce Radiant Earth to those of you who might not be familiar with. So we are a nonprofit organization. Our mission is to empower organizations and individuals globally with Earth observation, training data, tools, and standards so that the community who is using the machine learning and Earth observation can meet the world's most challenging problems. And we envision basically leveraging the ML techniques and Earth observation data to have a global positive impact. Our work is focused particularly after a pivot last year on what we call machine learning commons for Earth observation. We have three pillars of work. The hub, which is the Radiant ML Hub, some of you might have heard the name, which hosts Earth observation training data sets. It's open access. You can access all the variety of training data sets we have on there. We can also host your data if you have data you want to share with the community. On the roadmap, we have planned to host also machine learning models. We run competitions on the data, recently finished one of them on a Zindi platform as part of the ICLR conference. And we work on image annotation and ground referencing tools for generating and advancing training data sets. The second pillar of work is the community. The event that we are doing today is part of that. Convenings around developing standards and best practices for these techniques. Working on interoperability of data sets, technical working groups, and white papers are all part of the community effort. Last but not least is the educational effort, which is around sharing best practices around the latest advancements in the ML and EO techniques, news, market information, speaking engagement, and basically media outreach. And we have been working on these topics for a couple of years now. And we are really happy to work on the ground reference data guideline for the ag community particularly. But before getting into the guide, the question is, why do we need ground referencing? As you know, some of you have been working probably with Earth observation data. These data are available globally with the same quality, with the same temporal and spatial resolution. But for building machine learning applications and models in particular on these data, you need reference or label data, the term is used interchangeably, to build these models and also to validate these models. Some of the applications allow you to basically annotate an image and derive those labels. But in many of the applications, particularly in the agricultural literature, problems like crop type detection, crop yield estimation, or disease and pest detection, even with very high resolution imagery, you cannot identify the labels you are working for. Therefore, we need to be on the ground, collect data regarding these applications like crop type and crop yield, and then match those with imagery so we can build a model. That's why the ground referencing is required. The guideline that we are talking about, you probably have seen the URL in the event invite, but it is sitting now on our GitHub repository. So if you go to the bit.ly ground reference guide, or simply navigate to our GitHub account, which is with Radiant Earth, you will see a repository with ground referencing guide. The actual guide is the RST file that you will see there. All the information are included. I'm going to go over the main topics of that in the next 10 minutes. So in this guideline, we define basically 5 principles. The first one is about geographic specificity of the data. Then the class consistency, metadata, which is really essential for replicability of the data. Licensing and clear definitions of the license of the data. And finally, a well-structured format. But what do each of these mean, really? So when we talk about the geographic definition of the data, and this is a very common pattern across many of the data sets that we reviewed before defining and proposing this guideline, the data set and each record in the data set should include a very specific coordinate. For example, if you're mapping a farm field with all the information like the crop yield, crop type, the planting dates, harvesting date, you need to also collect where that farm is located. So a specific coordinate for that farm would be essential to be able to reference that record and then match it with imagery. It's also well understood that some of the times you want to anonymize the geographical locations. And this is acceptable, but that record should be already matched with another image that can be then shared with the community so the end user can really use the data along with an imagery. If you haven't matched or basically mapped the ground reference data to an image and then anonymize the location, there's really no way to match those and use those data. The geographic location should refer only to one class, meaning that if there are 2 types of, for example, crops within a larger farm, it is ideal if you can have reference coordinate systems for each of those separately. So for example, if there's maize and wheat in a farm, if you can separate them into individual boundaries and polygons, that would be the best recommended thing. It should be a discrete geometry. Again, the polygon should be very, very specific. And also it should refer to specific and discrete geometric areas so that you can easily identify on the image which pixels would fall within the geometry, which of them would not. To show you some examples of what we mean by these and what are the do's and don'ts of the geographic definition, as some of you who have worked with like GPS devices, when you're on the ground collecting a polygon or any other shape, there are 2 types of GPS devices. One of them that actively collects a point as you walk around. We call this active trace on the left side. In this case, when you walk around the field, the basically device is continuously collecting points, so you capture this field boundary completely. But there are cases that the GPS doesn't collect the points regularly, and you need to manually basically ping a point and then record it in your database. In those cases, it's essential to capture all the corners of a field so we don't miss any corner and we don't basically overlap with another field. So in this case, the active and manual, both of them are really good solutions, but we should ensure that all the corners of the field are captured. The don'ts in this case is basically don't missing any corner. So if you see this example, for example, the collector forgot to capture these green points, and for that reason, this extra region of the neighboring farm is collected in this polygon, which doesn't have necessarily the same label and properties as you're collecting in the target field. Unclosed shapes has been very common in the data sets that we have seen. Sometimes you map, for example, field A, and then you want to go to field B, but the polygon isn't closed in the first field, so it will continue to collect points, particularly with active trace. This is a common pattern. And then you, unfortunately, create a polygon, which is basically two fields, not one field. Some of these will happen in practice, and it's completely OK. But the point is, when we are doing like data cleaning or cataloging the data, these are the things we will look to ensure that the data basically has the best quality. So these kinds of information would be basically retracted from the data set before being shared. Another common practice in collecting data is due to basically extensive time that is required to collect the field boundary, is to collect just one point. In some cases, that point is within the field. So for example, the collector goes and stands in the middle of the field and collects one point with the GPS device. Or sometimes they basically stand outside of the field looking at the farm, either from the road or from a basically gate or something, and then collect that point. Again, that is an acceptable practice, but there should be a post-processing after that to use, for example, a recent satellite imagery, particularly if it is high resolution, to identify what is the field that that point basically corresponds to, and then convert that point to a polygon. If it's possible to map the whole field boundary using the imagery, that is ideal. If not, two recommended ones is just a shape within the field is acceptable. So as long as the polygon that you draw has the one class property, so it doesn't overlap with the neighboring farm, but it is smaller than the actual field, that is acceptable, because at the end, we need samples on the ground so we can build models or validate those models. Another recommended practice is to assume basically a fixed distance sample from that point. So capturing that point in a way that throughout your data set, for example, a radius of 10 meters is always within that field. So you don't need to necessarily map all these polygons, but you have a circle with a fixed radius across your record that matches all the fields. But that should be ensured that it is basically acceptable across all the records. In this case, the don'ts, again, is the partial overlap. So sometimes when you're mapping two adjacent fields, it's common that the GPS has an error, even within meters. That is very common, particularly depending on the type of the weather or where you are around the world time of the day. So these overlaps need to be, again, clear, that we don't have any overlapping polygons at the end in the data set. Because particularly when they have different classes, which is not uncommon, that will cause kind of a disagreement, and we don't know what kind of label you should use for that pixel. And also these kinds of what we call inconclusive points, that you have this point with that definition of the radius, but it's actually covering more than one field or one type of land cover. In this case, you see some forested area adjacent to the crop plant. So all of these are kinds of do's and don'ts of the geographic definition of a data set. We have a more detailed version in the guideline, but these are really the key points that we need to cover before collecting the data and also before sharing the data. And many of these can be incorporated into the data collection system. So you don't need to necessarily adjust for them every time, but designing the data collection in a way that we cover these is really a key point here. So the second principle was the class consistency and having clear guidelines on how each record is classified. This is really a key point. The records should be very specific how each class is identified. There shouldn't be any disambiguity between the different classes. A very interesting topic here is the intercropping patterns, very common in the developing world with smallholder farms. So if that is the case, and you have a farm that has different crops growing within the same field, and it is what we call intercropping, that should be a discrete class for itself. It shouldn't go with individual classes of those crops, for example. And for variables that are continuous, like the crop yield, it is essential to include accuracy and precision of those measurements. Those are required in a more preferred practice. It's good to follow kind of a well-formed and community identified classification schema. For example, for crop types, you can use the FAO AgroVac. When there is no consensus schema, that should be documented and well established before going to the data collection. And also for measurements like the crop yield, documenting how the crop cut process, for example, was performed on the ground, it is essential so the end user can understand the data and the quality. The third pillar is the metadata. These are the basically top metadata that is, again, essential to make sure the data is reproducible and replicable, and also it can be referenced correctly. Having the date coordinate system, so having the geometry was essential. Now you should have the coordinate system for that data. How the data collection was done, the methods for that, which is more of a descriptive definition here. Classification fields should be identified specifically. For example, you did crop type, crop yield, dates of the farming, or if you collected land cover class or other fields. Organization that collected the data and contacts of individuals who can be reached out to ask more questions about the data. Definition of those data fields, so sometimes they're not very clear, so it's good to explicitly identify them. And as you see, these are really metadata at the dataset level. You don't need to have them for each record. Description, if you want to be more detailed about what is this dataset about, what was the impact, who funded it, and other information you want to share with users. Consent, this is a topic that talks about, okay, if you're collecting data from like an individual farmer, if needed, depending on the data set and the applicability, you need to also share how the consent about that sharing is received from the farmer. So that should be identified. And last but not least, license of the data, which is actually the fourth principle of the guideline. The license should be very specific and clear. What are the things that the data can be used for, and what are the things that it cannot be used for? There is very common definitions for standards. Creative Commons has a variety of different licenses that you can adopt. We recommend generally Creative Commons by 4, which is the basically open source without any restriction for datasets, so that your data has the maximum impact and people can use it for different applications. But depending on the basically application you have, who funded that, you can apply different levels of licensing. But again, it should be very explicit and clear in the metadata. In the licensing, it's also good to note that the data should only be shared if the practitioner has the right and the permission to share that data. So that comes back to the consent information. If you don't have the permission to share the data, you cannot license it out. So those are the considerations that you, if you're the data collector, basically need to take into account. And if there's any anonymization that should be done on individual identities, that should be taken care of. Lastly, the well-structured format of the data. The data should be shared in a format that is well-defined. Any of the geographic definitions can be used, like GJSON, shapefiles, CSVs, or others, but it should be well-documented and a good format. And when it is possible, we generally recommend GeoJSON for 2 reasons. One is that the data and the metadata can be contained in a single file, so you don't need an auxiliary file for the metadata. And also the GeoJSON is compatible with many of the standards, as you know. And this sample GeoJSON, which is on the same GitHub repository, is an example of the type of data that we would expect to see in different data sets. This is on the same GitHub repository. When you go, you can explore and see different features. And let me share the screen so you can see that. Yes, so this is the GeoJSON file on the repository that you can see. It's an example of a field with crop type information and other metadata like the planting date, harvesting date. That was just a sample data set, but just as a reference, so you know what we mean really by GeoJSON data in this case. With that, I would like to thank you all for joining us today again. Please get in touch with us. These are the links to Radiant's website and our Twitter account. The GitHub repo that I mentioned, it has this ground reference guide and some other applications. And also we have a community Slack channel for Radiant ML Hub, which you can join at bit.ly ML Hub Slack. It's a community, it's a forum. You can connect with other users and also discuss topics of interest around the ML and Earth observation and ground reference guide. With that, I'm gonna invite Kai to present his talk. Kai?
Yes, so
if you can share your screen.
Good afternoon, good evening. Can you see my screen?
Yes, I can see and I can hear you. Thank you.
Good. So my name is Kai Sonder. As you can see, I work for CIMMYT, the International Maize and Wheat Improvement Center based in Mexico. And I'm giving this seminar on behalf of Jabu Ku, my colleague from IFPRI, who's in Washington, but at the moment busy in another meeting, unfortunately, but he's been working a long time on this topic, myself too, so he asked me to take over. We work for the CGIAR. Some of you may have heard about this. And can you see the second slide now?
Yes.
Good. So the CGIAR, for those of you who have not heard about us, we are a group of 15 research centers. About 8,000 people overall work here all over the world on topics in development, agriculture, crops. Most of these centers have different mandates, as you can see. In our case, CIMMYT is working on mainly on maize and wheat and some agronomy topics. We have the Rice Research Institute in Philippines and quite a lot more. A lot of this work dedicated to plant breeding, water management, food policy, lots of other issues, plant genetic resources, climate change, is lab-based or station-based. A lot of it is on farmers' fields, or economists, sociologists, anthropologists, other colleagues work directly with farmers with extension systems all over the world, mainly in developing countries. So we cover a lot of this. That also implies a lot of field work, a lot of data being taken on a daily basis, and not all of it, unfortunately, is georeferenced in a proper quality. I'm an agronomist originally, and I've been working on spatial issues as a data scientist, maybe a GIS expert, for the last 17 years, let's say. So I've taken a lot of georeferences myself, and I've suffered a lot under data that was not properly georeferenced and not georeferenced at all. So that's been a topic that's been discussed in our community of practice. All these 15 centers have GIS specialists, machine learning specialists nowadays, other people working on spatial data and spatial analysis. And we've been suffering under this topic for a long time, proper georeferencing, quality of data, consistency of that data. So this topic and what Radiant Earth is promoting nowadays is a lot more interest in using data that we already have that has been taken for machine learning purposes, for other things, crop modeling and so on. So we have a lot of interest, and it's not always possible if these data are not taken in a proper way and with proper standards. Very important. As you can see, we have a lot of work on the ground going on. This is not all of it, but a lot. There's an estimation that every year the CGIAR surveys about 180,000 smallholder farmers. In many cases, we have then proper data sets linked to either the farmers' locations or their fields. In these cases, standards, agreements. We have to have permission, as Ahmed has already mentioned. So we have a lot of these, and not in all cases the quality is very good, and they have to be properly stored also. But there's a lot of potential in utilizing these data and the background data, secondary data, for a lot more analysis in research. Here are some examples of work that has been going on. Our colleagues at ICRISAT in India, Cardam and some other colleagues, they have done lots of ground truthing, very large investments and remote sensing work, crop detection, field boundaries, all these things. So a lot of data collected in proper standards, These were of course done then by people who are properly trained, had the necessary tools, and had a purpose in what they were doing. So, but in many other cases, we can use data that's been taken for other purposes and utilize it then for more research. And smartphone crop phenology, more than 20,000 points taken by IFPRI, our colleagues also in India and other parts. Lots of potential to use that for calibrating machine learning approaches and algorithms and improve data sets that way. Here in Mexico, we have had a project that's been going on, Masagro, for about 9 years now. And every year, technicians and other people, farmers, extensionists that are linked to this project, they have been collecting data, in most cases very well georeferenced, was part of the work. In many cases, we have points for these fields. In some of these cases, we have field boundaries. And we're looking at the moment at ways how we can use some of these things to, let's say, to delineate field boundaries in an automated way. Some of these fields, they're 100 hectares, 80 hectares. So walking around with a GPS, as was mentioned before, is quite tricky. You can georeference off satellite imagery or other tools. You can derive boundaries using tools like Google Earth, but can be very tricky. It always depends how recent is the image. Not all of us have access to daily and frequent data, which still costs a lot of money, but it can be done. So if you have a good knowledge, or as was mentioned, if you have 4 boundaries at least for regular plots, it is relatively easy to be done. At the beginning, we had a lot of problems with quality of georeference in this case. Many technicians were not properly trained. We did a lot of training with those technicians, extensionists. A couple of thousand of them went through basic training on GPS and georeferencing. Having GPS at that time was a problem, which nowadays is a lot easier with smartphones. Most people use one of those, have a GPS of the same precision included. And we've been using the points you can see here, we've been using them for crop modeling approaches together with YASA, with some other people. We've been using them for testing algorithms for field boundary detection, for crop detection. We've been using them for economic studies, climate change, mitigation studies, and so on. So there's a lot of potential once you have properly georeferenced large amounts of data and you have it in well-managed, well-referenced databases, then you can extract a lot more, but it has to be done. So maybe some of you can guess how much of our activities in the field are actually georeferenced. I don't know if somebody wants to take a guess. I see here 10%, 20%, 60%. We estimate about 20%, which is not a lot given the amount, and has led to quite some frustration. Sometimes we have colleagues who come and say, oh, we have this fantastic database, we want to do a lot more. We know there's a lot of value in there for, let's say, plant disease modeling on wheat rust or something like this. And then when you start digging a bit, you see that, and often it's not properly referenced. We don't really know exactly where it was taken, or the quality is very poor because there were many people involved in the georeferencing, no proper training applied, and you have mixed coordinate systems, and it is a problem there. So 20%, and might be less, might be a bit more, but it has to be improved. Obviously, it's one of the big challenges. So Davu, in the last couple of years, he has been thinking about, we've been discussing that in the community of practice. He and some colleagues in the US and in Canada did a survey, and they asked a lot of researchers, why do you georeference, why don't you georeference? And you can see here some of the results. Most people, most researchers involved in this, most of them obviously not geospatial experts, but breeders, physiologists, agronomists, other people. The main reason was it's not really necessary for our project. If you don't think it's really necessary for your project, why should you invest even a couple of seconds or a minute to georeference this? side problem. So it's an issue about making people understand, telling people that any georeferenced data you take in the field has a lot of potential to be used for other research and development activities. Next reason was privacy and security concerns. I remember I worked in Ethiopia in 2003, and taking pictures in the landscape sometimes was very risky, especially if there was a bridge around. And also use of GPS in some countries at that time was totally restricted. Luckily nowadays, it's not that way anymore, but we can see similar concerns nowadays also with the use of UAVs. Lack of training was also a concern. And we've seen what can happen when training is not properly given, or there's no training at all. And you get a lot of problems, and you have to spend a lot of time and money and people's hours on fixing those data. Technical difficulties, lack of incentives. Here again, more information would be interesting. Policy or regulatory reasons or others. So researchers collect their own data. Sometimes you have people who go weekly to a site, but if you ask them to identify it somewhere on Google Maps or so, they're not really able to do that. If they would use a GPS, it would be very easy. Few researchers outside of data scientists maybe and other communities, crop modeling, they use or reuse existing data. Nowadays it's changing a bit because a lot of data sets have shown that potential. And there's no policy at the moment that compels CGIAR researchers to produce or share georeference data. We have policies that basically we have to share data once it's published. It's part of the open access data policy of the CGIAR and most of the centers. But for georeferencing at the moment, there's nothing fixed in place. So that creates another problem. How can we change the research culture? Implementation. So make sure that there's infrastructure in place to support those who want to change already. Make GPS, make apps for phones, make ODK available to everybody, make sure that everybody in the research institute, in the research community knows that those are around, and make sure that everybody can use them and that there's easy ways to upload that data and get it into databases. The same for interfaces, easy workflows that bring supporters of change, make it as easy and as simple as possible so people with no previous knowledge about coordinates, about mapping and other things, that they are able to do that easily without problems and without any data pollution. Norms, so informal understandings of what are good strategies, what are good standards, and bringing along the community. So what Radiant Earth is trying to do, very important step in this direction. So only if you have norms and people adhere to them, and you can share those data easily and can use them much more easily. And incentives, in our case, it's relatively easy. I can go to a colleague and say, well, if you have georeference data from the field, I can take a different look from it, from a different angle, and we can have a publication. You will be a co-author, and we can do a lot of additional things. So that normally helps quite a bit. And once people have done that once, they will be much more ready to georeference properly and share the data the next time. And then policies at an institutional level. Most institutions nowadays have data policies, data sharing policies, inside and outside. In our case, for example, we have 2 years to publish data. After those 2 years, that data has to move into a repository for the institution and for everybody else. Can be Dataverse, can be anything else, but it has to be available. And then we've had cases already where colleagues, let's say in UC Davis, have just downloaded data and done very interesting things with ground truth data that we had never thought about. So very interesting too. And if you have a good policy that is also enforced and has enough incentives that people actually adhere to it, then you can have a lot of additional benefits. These two, very important in the sense, so nowadays there's really no excuse anymore to georeference. I think in my career I've bought probably way over 500 GPSs. And the last 2 years we stopped doing that. Why? Because almost everybody carries a smartphone nowadays. I used to carry a laptop, a GPS, a phone, and lots of other things. Nowadays, in many cases, I only carry the smartphone because it can do a lot of these things. GeoODK, very interesting tool suite that many of our colleagues, also socioeconomists, are using to georeference data, and it fixes also a lot of problems that we had in the past, that people would take coordinates with a GPS by hand, write it down on paper, and someone in the office would transfer it to a database, Excel, or Access, or anything else. And then you would have lots of human errors. So the more direct you can go to data entry, if you can combine data on a tablet or a phone and then get it directly from the GPS into the database, then that human error and any issues with coordinate systems and so on is already fixed. Here we've been using this Mapit.js for Android phones. Very simple, very cheap, very practical app. There's plenty of others around also for Apple products. So there's really no excuse not to do that. I remember last year I had a colleague who came from a survey in Haiti, and she came into my office and said, "Oh, you will be angry at me because I need you to make a map." And I did the survey on a maize virus, but I didn't take a GPS. And I said, "Well, I'm more angry because you actually took your phone and you didn't use it." Yeah? So at the end, it took me like a week to get georeferences for all the village names she had provided, and a couple of those we never found because there's no proper databases. In many countries, place names are exactly the same, so very difficult. And I think that was it from my side. Very important to have proper standards, and we really need to get more people to georeference in a proper way so we can get a lot more value out of data and share that across extension and research communities. Thank you.
Thank you, Kai. Very great presentation on the CGIAR activities, and thank you for bringing the discussion to the implementation part, right? Where we stand in the community, particularly the community that CGIAR works with in terms of data collection, and where we need to go in terms of getting better at doing the ground referencing and then the cataloging and sharing of the data. So I see a series of questions. That's good. So we are going to start from the top and go over them. We have good amount of time to cover them. The first one is about what are the requirements to access the ground data of agricultural land in West Africa. I believe this was one of the data that Kai showed. Can you talk, Kai, briefly about what is the requirements to access any of the data sets that you shown from the big data platform?
So as long as these data are already available, I think there's a web search engine that was created by the CGIAR. It's called Guardian, G-A-R-D-I-A-N. Google it, and most of the data sets in the CG that are already out there that can be found in Dataverse or other places, they would be available there. But send me an email, please, and then you can have a direct look at what you need, and I can put you in contact.
Yeah, thank you. And on the Radiant ML Hub side, I can say we don't have still data from West Africa in particular, but other data sets that we have, particularly more on the East Africa side, all of them are open access. Similarly, you can go to Radiant ML Hub. You need to sign up, but the sign up is free, and then you will use the API to search for data and access them in any environment that you are working. The next question is on, let me highlight the ones that are more on the ground referencing one. So what are the expectations of accuracy in georeferencing? A follow-up question on that, because we talked about the phone GPS, is if the standalone GNSS accuracy, like the 3 to 5 meter, is good enough. I will share our experience, and then I will have Kai also comment in here. So we work with one of our partners to compare the accuracy of a Garmin quality GPS device and a cell phone one to map farm fields in a smallholder region, and they were relatively good. Both of them were being mapped to the same basically farm that we were looking at the high resolution imagery. The key decision point here is how you want to use the ground reference data. In our application, we were interested to map those data into the Sentinel-2 satellite imagery, which is 10-meter spatial resolution. So in that sense, a phone basically GPS accuracy was good enough for us. But if you're interested, for example, use the 30 centimeter very high resolution imagery, maybe then the 3 to 5 meter accuracy is not good enough. You need to be a little more high quality. Having said that, you can usually use those ground referencing that you have from your phone device and then post-process them, quality control them, and correct them if needed on the imagery, and then make them basically a benchmark ground reference data. Kai, you want to add to that?
Yes, I mean, we found that in most cases, normal GPS accuracy is enough. We're talking about very large areas. What is important, though, is that, as has been mentioned in the Radiant Earth presentation, is that points, for example, clearly define one field. I've received points where they were like in the middle of 4 fields because people just drove somewhere and then you had a dirt track and the point was somewhere on the dirt track, so then you don't know which of the 4 fields. In those cases, obviously quality is an issue, but as long as the point is clearly in the field, I think that's good enough. When combining these kind of things with UAV flights, we've been using RTK, so high resolution GPS units, but the cost is still prohibitive in most cases. So that depends a bit on the research implementations, but I think overall, as long as the accuracy is good and the field or any place that we want to characterize is clearly identifiable, that's good enough.
There's another question on the minimum crop field size for doing ground referencing, and they reference particularly in India, there's high crop variability even in a hectare. So what is the suggestion for that? So we have a suggestion in the guideline, particularly for using the ground referencing data with open satellite data. We recommend that field collection is at least 20 meter by 20 meter. This is really the minimum you should do. Otherwise, it's really impossible to use the data. So that can be mapped to an open satellite data. And if you have high resolution, then it will be even better. Yes, crop variability is a common pattern, not just in India, in many parts of the world that are smallholder farms. And for that reason, we have some recommendations, particularly if the field is intercropping pattern, you can identify multiple crops for the same size. If it is hard really to basically have different polygons for each of the portions of the field, you can map the whole field, but then identify, for example, this farm has maize, has, I don't know, beans, wheat, or other types of crops within the same polygon. If it is possible to distinguish those plots within the farm from each other and then have different crop labels, that is the recommended practice. But we know that is really hard to do in many cases. So yes, a minimum 20 by 20 is really what we have seen, the minimum requirement for to be able to use the data really with the imagery and build models. Another question is, what are the factors to be considered when collecting the data to building ML pipelines for crop classification? So the 5 principles that I discussed and we have in the guide are the collection of basically requirements for doing the data collection and cataloging them so they are useful for ML pipelines. But the top priority ones, particularly if you want to use the data internally yourself, is really having the right geometry and geolocation there, having the right polygon, being specific, and each record of the data is really an individual crop type. It's not like a mix of farms. Having the dates recorded is really essential, particularly if you want to do crop type mapping. It is good to know what is the cropping season, right? When did the plot that you were doing the ground referencing did the planting and when they did the harvesting. So you have the seasonal pattern. Then you can use time series of like Sentinel-2 or other satellites to do the crop mapping. And other information that I mentioned about like the classification definitions, making sure the collector who is collecting the data is well trained on the definition of the classes, right? If you're, for example, distinguishing between different types of maize on the field, those are identified beforehand. So the collector doesn't need to make a decision when they're doing the ground referencing, what should be that class? So those should be really well defined in advance. So there are some efforts here that if you put into the collection before going into the field, it will really enhance the value of the data, and then you can easily use them in different applications, including building ML pipelines for crop classification. There is one that I think, Kai, you can also comment in. To what extent are you finding drone imagery useful? And have your organization, would your organization be able to consume high resolution, like around 2 centimeter ground sampling distance, and highly accurate and georeference data from motion derived products? Have you had any experience with that, particularly with drone?
So yes, we have used drones initially for things like high throughput phenotyping on research stations to speeden up breeding processes. And then some of our colleagues are also using it for land use change mapping, getting high resolution elevation models and those things. And so it is obviously very valuable data. It opens another can of worms, basically, in terms of it's a lot larger than most other remote sensing data. You start using drone data, then you need to think about backup systems and so on, where to store it, how to handle it. In many countries, restrictions are getting worse. So here in Mexico, for example, on our main breeding station, we cannot fly anymore because we are too close to 5 small airports, which made a lot of investment then useless. But overall, it's very valuable data. It can be incorporated. I think there are some websites already nowadays where people share drone data freely, also so that other people can use it for different purposes. I don't know exactly which data you're referring to with the motion derived, but I think, yes, generally we can use almost anything. I'm very excited at the moment with products coming from satellites with daily revisit times and at higher resolutions now. Still commercial, but if you've seen the movement in satellite imagery over the last 10, 15, 20 years, it's amazing where we've gotten nowadays. Something like Sentinel-2 is already an amazing step forward. Years ago, we had 30 meters, was good. Now we have 10. We can already buy 3 meters on a daily basis. You can buy even smaller amounts. And then in many cases, you can fly very quickly and cover that. So yes, very useful. And I think we can ingest almost any drone data or UAV data that is available freely.
Thank you. So there's another question which is a bit in a stretch for the discussion of this topic, but I think it's good to address it and then provide references. And the question is about how to decide on the number of ground reference data that needs to be collected for crop classification. So that is a very common question. It is a very good question, but it really deals into the, okay, what model are you using? Where in the world are you doing that crop classification? How homogeneous or heterogeneous is that region? And what is the size of the farms, basically? So there is no like absolute number that you can put on the ground referencing and say, okay, this is the number of fields or the points I need to collect so I can build a crop classification model. But the factors you need to take into account are what type of a model you're using. Even in the machine learning techniques, there are a variety of models from random forest to like convolutional neural networks. So depending on what model, that really impacts the number of samples you need. As I mentioned, how homogeneous is your region? Is it all maize, for example, or you have 10 different crops? If you have a variety of crops, you definitely need more samples, and you need more samples per class. So you can basically capture the dynamics of those. If the crops have very similar phenology, then you need more data to be able to distinguish those types of crops. But if they are very distinct, if the seasonality is also very distinct, then you need fewer samples for that. The size of the plots matter. If the plots are larger, so you can capture larger polygons of the same crop, so you basically have more pixels in the imagery with the same label, that really helps. So that is a factor to take into account. And lastly, it is really the knowledge of the person from the region who is doing the data collection, right? particularly for, let's say you're going to a village, you want to do ground referencing of the farms in that neighborhood. It's really a decision of the collector to make sure they capture the diversity of that region, and they collect data not from one portion of the village or the farms that are very adjacent to each other, but throughout the village, so you have a representative sample. That representativeness is a key factor there. One other point to consider, and I will give you a reference for that, is methods like transfer learning, that you can potentially build your model in a different region, but then use fewer ground reference data in your target region, and then fine tune your model so you can have a better accuracy. You can very soon have access to a report out of a workshop that Radiant hosted with NASA that talks more about really building models and focusing on the requirements for the model building part. That will have a lot of references about, okay, how people have used this in the community and what are the recommendations for next efforts. We will share that report soon on our social channels, and you will have access to it. It's an open access report. So let's see the next question here. Actually, we have multiple of them. So the question is about, do you have a system in place to validate each other's data, for example, similar to the Collect Earth app, where others can also check if they agree with your labels? I will let also Kai talk about CGIAR. We don't have an automatic system in place yet, but because we are doing this the way we talk, that everything is georeferenced, we have the time and everything, there are easy ways to programmatically basically match those ground reference data against each other. The difference with Collect Earth is that we are not doing any visual basically data collection. There is no annotation happening here. It's really ground data being matched against imagery. So we can actually compare the ground reference data from two different efforts or two different campaigns and then see how they match or they don't. We can programmatically do that. We sometimes do that for quality control before sharing data on MLHub, but there's no, I would say, live application that you can do it on your own. Kai, do you have anything in place for that?
No, we don't have something like that yet. It would be very useful, obviously. I've seen some examples in the wider community where people have used crowdsourcing and so on to cross-validate. In our case, it's that most of the data we are taking is not specifically designed or done for machine learning examples. So that will have to be implemented at some point, I guess, yeah. And to see also how you can incorporate more for other purposes to be more useful in that sense, yeah. But very valid question, very important thing that we would need.
So there's a question that I want to also briefly talk about it. How to safeguard study participants' anonymity, which is an important ethics guideline for research with human subjects. Continuing that georeference data might give away people's identity anonymity, which seems to be conflicting with the objective of having a precise GPS coordinate as possible. So one of the things I didn't explicitly mention at the beginning was that this guideline is really focused on the technicality of the problem, not necessarily on the policy and ethics of it. But that is a very good question, and it is a good question that we are actively working with the community to find solutions to it. Depending on where you are in the world and what type of data you work with, that basically question can be addressed differently. And there is a need from the community to define what are the basically human identifiable data. On Radiant side, we don't share any information on Radiant ML Hub that has any identification of a human or a person, basically. Whether it's name, whether it's any of their personal information like date of birth or anything else. The GPS coordinates are shared with the data as long as we have the consent from the data provider that that is okay. So those are shared in those places. But this is a very good topic, and we will be engaging more on that from Radiant side with the community to have a better understanding of what are the basically different aspects of that, what are the benefits of sharing data, what are the downsides, and how can we address these concerns about basically ethics and the consent of the farmer or any other individual who we are collecting data from. Kai, do you want to add to that anything?
Yeah, good question, Berber. Thanks for that. Very tricky part. Nowadays, it's obviously very easy to collect data without asking people. I can do that from my desk anytime I want to. So you have to be relatively careful. In many countries, if you have a field location, if they have a working cadastral system, it would be very easy to catch somebody. I've heard about some examples where people were extorted because it was possible to identify farmers who had received subsidies, you know. So indeed a very tricky thing. And as Ahmed was saying, that you have to make sure when you take the data that you have the consent. That's the easiest one. And in some cases, in some political environments, some countries, you probably have to think very hard about whether to share it or not. Obviously, what you do in socioeconomic studies, you just reduce the precision of the data point. That is also very risky. It makes it obviously then useless for a lot of other purposes, but it has also the risk that it may point to somebody else's house or field. So I find it always interesting that you can reduce the precision, but you can create other problems with that. But it's a topic that has to be discussed a lot more, and we probably need very clear guidelines also on the legal side to make sure that there's no problem there.
Thank you, Kai. We are at the top of the hour. Thank you, everyone, for joining us today. There are a couple of questions that we didn't get into, but we will be happy to discuss with you individuals about those. If you want, you can email us or you can join our Slack channel, ask the question, and we will definitely have a conversation there. Thank you, everyone, and have a good rest of your day. Thank you, Kai, for also joining us.
Bye-bye. Thanks a lot for everything.